So as we begin Module 8, we're going to be taking a look here at our finite difference equations, specifically looking at our nodal network. Within this, we're going to be taking a look at transient conduction and the lumped capacitance method right here. So an overview, within this module, we're going to take a look at the finite difference equations and consider the nodal network as a method to determine temperature distribution. So this is going to be wrapping up our Chapter 4. Then we're going to get into Chapter 5. We're going to start developing procedures for determining the time dependence of temperature distribution within a solid during a transient process, as well as for determining the heat transfer between the solid and its surroundings. So some objectives within this module here. We'll be taking a look at our finite difference method, talking about our nodal network, going through our energy balance method, looking at transient conduction and specifically our lump capacitance method, and ending with our Biot numbers there. Now as this relates back to our textbook, this goes with our reading guide here now. For Chapter 4, we'll be looking at sections 4.4 and 4.5. And for Chapter 5, if we start that chapter there, it's going to be looking at sections 5.1 through 5.3. So as we begin our Module 8.1, we're looking at 2D conduction. In particular, we're going to be looking at our finite difference equations. So within this here, we're going to be utilizing our nodal network to determine temperature distribution. Within this, we're going to formulate the system of linear algebraic equations as a matrix equation and briefly discuss its solution by the matrix inversion method. So objectives within this first section for Module 8, our Module 8.1 here, we're taking a look at our finite difference equations. Within that, we're looking at our nodal network, talk about the finite difference form of the heat equation, and look also at our energy balance method as well. We're also going to do some solving of the finite difference equations, looking at the formulation of our matrix equation, and then verifying the accuracy of our solutions. So activities in this module here, we'll go over the theory along with all the topics we talked about up here, go over some of the governing equations, talk about some practical applications, and then go through some of my hand solutions to these problems. So as I mentioned, the first section here, Module 8.1, we're going to be wrapping up our Chapter 4, looking at sections 4.4 and 4.5 in our textbook here, and this will relate back to two-dimensional conduction, specifically looking at our finite difference equations. So as we begin here, I want to discuss our finite difference method. So what is the finite difference method? Well, this is an approximate method for determining the temperatures at discrete or nodal points of a physical system right here. So within this, we want to come up with a procedure to follow this through. So our procedure right here is going to be represent the physical system by a nodal network. So that's the first step right here. That's what we want to do, is represent our physical system by this nodal network right there. And again, these nodes are discrete points of the physical system right there. Second step in our procedure right here, we're going to use that energy balance method, go back to our general energy balance equation right there, in order to obtain finite difference equation for each node of unknown temperature right there. So again, we're going to do this for each node separately. Last step in our procedure right here is we're going to solve the resulting set of algebraic equations for the unknown nodal temperatures right there. So we're going to develop these equations, look at what's unknown, and go through and actually solve for those unknown values. So this is something that's important for us for any type of problem that we're looking at here, is to come up with this general procedure for analysis. Whether it's something we've written down or something we can reference back to in our textbook or lecture slides or maybe some of our notes right there, this is something that's important to have. Having an organized set of steps to go through for procedures for solving different types of problems is very helpful. It helps us when we're staring at a blank sheet of paper and we don't know where to start. We can go back to our general procedure and say, oh, okay, these are our general steps there, and each one I can go in and look at the specific details related to the problem that I'm working on. So the next thing I want to look at here now is our finite difference approximation with our nodal network right there. So for our finite difference approximation, we're talking about our nodal network. The nodal network is going to identify these discrete points at which the temperature is going to be determined and uses specific notation. This is the m comma n notation. And this is going to be used to designate the location of those nodes right there. So as we relate this mn notation back to something we've seen before, we can think about our Cartesian xy coordinate system in 2D. So if we think about that right there, our x direction right here is associated with our m in our mn notation, and our y direction is associated with our n in our mn notation right there. So that is how we're going to identify these nodes. So if we look over here and we zoom in on this little square right here, let's take a look at this. Well, the center of this square right here is our node of interest, our mn node right there. So we can have that by knowing how far over we go on our x, how far up we go on our y. So for a specific one here, we can count right here. If this is our 0, 0 right there, for our coordinate system, we go over 1, 2, 3, 4. So we're over 4 in our x direction, which is our m right there. And we go up 1, 2 right there in our y direction. So we're up 2 in our n direction. So it's 4, 2 right there for our mn for the notation for this guy right here. Now, many times what we're going to want to do is associate this node with its surrounding nodes. Whether we're talking about conduction, convection, whatever it is right there, we want to know how we can work with those nodes right there. So having this mn notation to designate their location is very helpful, because we say if this is our node of interest, this is mn, and we know its location right there, well, then this node up here is going to be m comma n plus 1, because we're going up 1 in our y direction right there, where this one is going to be m comma n minus 1, because we're going down 1 from this mn location in our y direction. So similarly in our x direction, we can say this right here is m plus 1 comma n right there, because we're going over 1 in our x direction. This is m minus 1 comma n, because we're going over negative 1 in our x direction right there. We see our n doesn't change because our y doesn't change there. So now taking a look down below here at this graph right here, we can say what is represented by the temperature determined at a nodal point right there. For example, our temperature at mn right there. Well, we can use this finite difference approximation to represent the temperature gradients in the domain right there. So this is where we can see our temperature gradients right here, our partial of t with respect to x right there for our node m of minus 1/2 comma n right there. So we can see that's our m minus 1/2 right there, and then we can say the same thing, partial of t with respect to x right here of our m plus 1/2 comma n right there, so that would be this location right here. So if we're looking just in our x direction right here for this right now, we can say is, well, how do we locate these intermediate points right here? So if we know this is our m, this is our m minus 1, and this is our m plus 1 right there, and it's our temperature with respect to our x distance right there, this is the delta x as we're moving along in our x direction right there. Well, what if we want these intermediate points that are in between those right there? So we can say, well, what we can do now is we can say, well, our temperature at m comma n right there minus our temperature of m minus 1 comma n right there, all divided by this delta x right here, our delta x right there, is going to give us this temperature gradient right there in the center of that right there. Now we can do the same thing if we're going from our m right here to our m plus 1 over here. So we can say our partial of our temperature with respect to x right there of m plus 1 comma n right there is equal to now our temperature of our m plus 1 comma n right here minus right now here our temperature m comma n right there, and this is all going to be divided by our x term right there, our delta x right term, which is that delta x term right there. So this is how we can use this to find the temperature gradients in our domain right there by this relationship right here. So now let's ask ourselves how the accuracy of the solution is affected by the construction of the nodal network right there. So if we think about this, we go back up here and we think about this delta x right here, and we think back to our pre-calculus. So we're talking about finding the integral of a curve. So the integral would be the area under a curve. Now, how do we approximate the integral under a curve? Well, that's we could take individual rectangles underneath that there and sum up the area of all the rectangles, and that would give us an approximation of the area under the curve. Now, what we found in pre-calculus when we did that before was if we made those rectangles narrower and narrower, then that would be closer and closer and a better approximation to the actual integral to get that area under the curve. So the smaller we made that delta x, the more accurate our result would be. Well, what else did we find when we made that delta x smaller and we're doing this out by hand like that there? We would find, well, that's a lot more rectangles that we're going to need to calculate as we're going through that there, and that's a lot more intensive, a lot more work to do. So the same type of thing we can say down here when we're talking about the accuracy of the solution affected by our nodal network. So there's a trade-off between a fine or a coarse mesh as we're doing this here. So the trade-off is if we do a fine mesh, yes, it's a lot more accurate, but it's a lot more computationally intensive. So whether we're doing this out by hand and solving it analytically, or we're plugging it into a program and doing some type of numerical analysis to solve this here, either way, it's a lot more computational intensive. Either it takes a lot more computing power, or it takes a lot more time for us to actually go through and calculate it. Whereas if we deal with a coarse mesh, it does get us our answer a lot quicker and is a lot less computationally intensive, but our results are not as accurate. So you can see here our finite difference was known as an approximation right there. So if we want it to be more accurate, we would need a finer mesh. So as we move forward, the next thing I want to talk about here is our energy balance method right here. So if we're taking a look at the derivation of our finite difference equations dealing with our energy balance method right here, what we have now is the fact that this is a convenience that removes the need to predetermine the direction of the heat flow. So we assume that all heat flows are going into the nodal region of interest and express all heat rates accordingly. Therefore, we can use this relationship right here, which relates back to equation 4.30 in our textbook right here, where we have the rate of our energy transfer going into a control volume, which is our E dot IN right there, plus the rate of energy generation right there, which is our E dot G right there. So this again relates back to our equation 4.30 in our textbook, and adding those two together will equal to 0, which is our energy balance method right here that we're going to utilize. So one thing we do want to consider next here is the application to an interior nodal point. So this is our M, N nodal point right there. This is going to be our internal point. And this is a nodal point that exchanges heat by conduction with 4 equidistant nodal points right there. So if this is our MN right here, we want our 4 equal distant nodal points right there, we can see, well, if we go up here, then we have an M, N plus 1 because we're moving up in our Y direction, or our N direction right there in our MN coordinate system right there. So that's an N plus 1, going up 1 node in that Y direction right there. This is an M, N minus 1 because we're going down 1 in that direction right there. And then we can see over here we have our M plus 1, and we're going over in our X direction plus 1 to the next node right there, N. Our N doesn't change. And we go to the left right here, we find this node point over here, which is M minus 1, N right there to get to that nodal point right there. Now the other thing that we can take a look at and note here is the width of each of these squares right here is delta x and delta y. So delta x wide, delta y high, but then we can also notice here is the distance between these points. If we're moving over here is that same delta x right there, because the points are in the dead center of that square right here. For each of those squares, that point is in the dead center of that there, which also means that we have our distance right here of a delta y between the points in that direction as well. So now in order to find our heat transfer rate there, our heat Q value right there, we want to use the summation equation that we see here, where we have our summation from I equals 1 to 4, where I refers to the neighboring nodes right there. So this right here is our node, all of this 4 right here, 1, 2, 3, and 4 are our 4 neighboring nodes right there. So that's what our I value is for on the summation right here. And this is as our Q sub I goes in to our M sub n. So each one of these, you can see the arrows going into that center point right there, our M sub n right there. So again, M sub n is our interior nodal point right there, which is the one that exchanges heat by conduction with these 4 outside points that we're considering here with our I is equal to 1 through 4 right there. Now that is going to be added to our rate of energy generation per unit volume right here, and that's where we have now our Q dot right there, and this is times our delta x delta y times that L value right there, and this is going to be equal to 0 right there. So that's us being able to plug in now to this equation up here from 4.30 in our textbook right there, where we have that rate of energy transferred into a control volume right there, plus our rate of energy generation right there, our E dot sub G right there. So right there is where we're getting that term from right there as we go into this equation here. Now, this is our very general equation right here that we're looking at. Let's go for a specific example right here. So let's say if we want to go from this node right here of Qm minus 1, n. So this is our Q of m minus 1, n right there, and this is going to our interior nodal point right there, m, n right there. So we're coming in from there to there. So let's apply that to this equation here. This is going to be equal to our K, which is our thermal conductivity right here, times our Y delta YL value right there, or sorry, delta YL value right there is going to be the quantity right here is the heat transfer area. And this is going to be multiplied by this term right here, where this term right here is going to be the finite difference approximation to the temperature gradient between the boundary of the two nodes right there. So that's where you can see those two nodes. So that's the temperature of this node right here minus the temperature of our interior nodal point right there, m, n, all divided by that distance between them, which we've just shown is a value of a delta x between those 2 points. And this relates back to our equation 4.31 in our textbook. So the next thing I want to consider as we continue on with our energy balance method right here is our table 4.2 in our textbook right here. So this gives us a summary of finite difference equations for common nodal regions. So within this here, let's just pick one of these common nodal regions and take a look at it specifically right here. So let's consider an external corner with convection heat transfer right here. So this is our problem right here, and this is taken directly from that table 4.2 in our textbook right there, where there is our M, N node right there that we're interested right in. Now we can see our surrounding nodes right here. Well, we have our M minus 1 N over here and our M, N minus 1 right there. And we can see the distance between these nodes is delta X in this direction and delta Y in this direction here. And now we're dealing with convection heat transfer on the corner node right here. So there's our convection terms right there. There's our H value and our T sub infinity right there. So now if we use our energy balance equation and we sum those all up for all the nodes right there, so that's what we're doing right here now, we can say, well, we have this node right here, our Qm minus 1 comma n, and we have this node right here, our Qm comma n minus 1 right there. So we have our value for our heat transfer going to that, from that node to this node, and from this node into our node right there, Mn right there. Then this is going to be plus now. We also have our convection term over here from our surrounding fluid right here going into the node right there, which is our Q infinity going into Mn right there. So if we sum all these together with our energy balance method right there, they're going to be equal to 0. So now that we have this energy balance equation right here, what we want to do is look at each one of these terms in this equation right here and come up with our governing equation. Now, a way that we can do that is we can go back to this table 4.2 in our textbook right here, and we can take a look and see which case this is. Well, this is case number 4. It's a node at an external corner with convection. So it's exactly what we said we had right there, a node, external corner with convection heat transfer. So that's exactly what we have right there. So this is going to give us our governing equation 4.43 right there. So we have this relationship right here now. Now, a thing to note is this is for the case when our delta x is equal to our delta y. So if that is the case right there, we can utilize that equation from 4.43, which came from that table 4.2 in our textbook right there, and it tells us that our T of m minus 1n plus T of m and minus 1 right there. So the sum, the temperatures of that node right there and that node right there, plus now we have 2 times our H value right there times delta X all over our thermal conductivity times our T infinity right there. So now we have all of those terms right there, and we can see there's our H value that was given to us right there. There's our T infinity right there. So we can plug those values directly into that right there if this was a given problem with those values. Minus 2 times our H term again times that delta X over that thermal conductivity K plus 1 times now our Tmn is equal to 0 right there. So again, based upon what they give us, what we're solving for, we can utilize this relationship from equation 4.43. Let's just say we had all the information of the surrounding nodes right there, and our H values right there, and our surrounding temperatures, and our thermal conductivity for that type of material right there. Then we could solve for our temperature of this node of interest right there. Now this could be work different ways as well. Maybe they gave us that and we're trying to find one of the surrounding nodes, or maybe we were trying to find the surrounding T infinity temperature right there. Either way, this is a great governing equation right there. But the thing to note is this is for when delta X is equal to delta Y. Now, if delta X is not equal to delta Y, then we have this relationship up here for the equation now. And you can see this is a little bit longer, more involved equation. So oftentimes when we have these simplifying conditions right there, it does just that. It simplifies down our governing equation from the general equation right there. Now, if you're not sure if your delta x and your delta y are equal, you can still plug this into this equation right here to double check that as well. So now let's actually go to that table 4.2 in our textbook right here. So this table right here shows us the summary of nodal finite difference equations right there. And take a note again, right at the top of this table, it tells us that assumption right there. These are the finite difference equations for the case when our delta x is equal to our delta y. So that is specifically for these equations right here. So those are the equations in this column right here for that specific case right there, our 4.29 all the way down to our 4.43. So for each of these cases right here, let's take a look at those. This is the case that we had right there, case 4, where we had a node at an external corner with convection right there. We can see there's our convection right there. There's that external corner right there. So it's a pretty straightforward one for us to figure out there. Let's start at the top. We could also have the case where we have case 1 of an interior node. So there's our interior node right there. We can see there's our 4 surrounding nodes, our m, n plus 1, m plus 1, n, our m, n minus 1, and our m minus 1, n right there. And we can see that's our delta x going right there from one node to the other, and our delta y going from one node to the other right there. And this is our corresponding finite difference equation for that when delta x is equal to delta y. We can say that the temperature of m, n plus 1, so m, n plus 1 right here, the temperature of this node right here, plus the temperature of our m, n minus 1 right there, that temperature node right there, plus our temperature of m plus 1, n, this temperature node right there, plus that last one, as you can imagine right here, our temperature over here of m minus 1, n. So that basically says the sum of all 4 of the temperatures for each of those 4 exterior nodes minus 4 times the center node right there at Mn is equal to 0. And that's that balance right there. That's equal to 0 right there. So again, you could move this over to the other side if that's what you're solving for, that Mn right there, and say that that is going to be equal to the sum of all of those divided by our 4 right there. Now we can also take a look at these other two cases. Case 2 is a node at an internal corner with convection. So opposite of what we saw in our problem right there, this is going to be an internal corner right there. So we have the following relationship for given this equation right here, number 4.41 for that case right there, where we have convection going on at that internal corner. And in case 3, we have the entire side of this right here now with convection. So this is a node at a plane surface with convection right there. And this is given by this relationship shown here for equation 4.42. Now, continuing on with our energy balance method right here, one thing that we want to think about now is our interface for contact resistance. Are we dealing with contact resistance or not? So this brings in the question of what if we have two different types of material right here, material A and a material B. So the thing we want to know is the potential utility for using thermal resistance concepts to express rate equations. So for example, right here we have conduction between two adjoining dissimilar materials. So there's that material A and material right there, two dissimilar materials, and there's going to have now this interfacial contact resistance between those two right there. So we can see this right here given by this expression that we've seen before, R sub T double prime comma C. This is our contact resistance between those two different types of material. Now we can see we still have the same node system set up right here. That's our node of interest right there, M comma N right there. It's got some width right there, delta X, and some height right there, delta Y right there. We have another node down here. It has that same delta X, delta Y dimensions to it right there, and this is now our M comma N minus 1 as we're going down in that Y direction right there. But now you can see that this node right here is purely in material B and has our thermal conductivity K sub B, and this node right here is purely in material A and has our thermal conductivity K sub A. So if we're looking at our heat rate going from this node into our node of interest right there, M sub N, this is going to be equal to our temperature difference between our temperature at this node here minus the temperature at our node Mn right there divided by our total resistance right there. Now what is our total resistance? Well, this can come from equation 4.46 in our textbook right there, where our total resistance for this problem right here is going to be our delta Y over 2 right there divided by, and this is material A right there, our K sub A, times our delta X times our L right there. And then we have now our resistance from our thermal contact resistance right there, R sub Tc, divided by our area again right here, our delta XL right there. And then now we have, and the last thing for our material B right there, our delta Y over 2 right there, divided by our K sub B times our delta X times L. Now, if we think about this, Y is our delta Y over 2. Well, this right here is a distance. In the center of that right there, that is a distance of delta Y over 2 away from that right there in both of those. So each of those has that distance of the node being away from that center contact resistance of a delta Y over 2. So that half of that right there, but it does have the full surface, our delta X right there, as well, not half it there. That's the full surface of our delta X width right there. So this is where we have our delta X times L right there for our bottom, our denominator for this relationship right there. So now this relationship here, when we plug in for this, is R total, can then go back up into this relationship here to get this value from this relationship in this equation system right there. So now I want to go through an example problem together, utilizing some of those governing equations and theories that we saw at the beginning part of this module. So right here in problem number 4.42, what they're asking us to do is to find the expressions for, right here, our node Qm minus 1n going to our center node there. So there's our center node right there. And this is Q of m minus 1n going in, like that right there. And we want to find now our Q value for our m plus 1n going into our N right there in the center again. So this is M plus 1N. So this one going in right here. So those two right there. And those we know are all on the interface between material A and material B. Then we also want to find now our Q of M comma N plus 1 right there. So this value right there going into a center right there for our heat rate going in there. And then we also want to find our Q for our Mn minus 1 going into that center node right there. And this is for conduction again through these two different types of material. We're going to be looking for the conduction associated with a control volume that spans these two different materials. Now, a thing to note right here that they're telling us to simplify this problem down is that there is no contact resistance at the interface between the two materials. So between material A and material B, if we come right here at that interface right there, there is no contact resistance that we have to worry about right there. So that's going to simplify down our solution. Now, it also tells us that the control volumes are L units long into the page right there. So it's going to go back in 3D like that there into the page, some distance L right there. So what are they asking us to solve for now? Well, they also want us to find the finite difference equation under steady state conditions. So there's another assumption we have right there. It's going to be steady state conditions for our center node right there, M comma N. So now that we've read through that problem statement and taken a look at what they're asking us to solve for, let's simplify it down just a little bit and figure out a procedure for analysis for this problem right here. So what do we know? We know we have a control volume and a nodal configuration in the vicinity of the interface of two different materials right there. Now they're asking us to solve for two different things. They want us to find the expression for the control surface rates, and also to find a finite difference equation for that center node Mn right there. So let's redraw this out with our heat rate equations for each one of these nodes right there. So we have our Q of Mn plus 1 going into the center right there, so we can see that's going in there. We have our Q of Mn minus 1 going into the center. There's that guy right there, and you can see there's an arrow there. Now we have our Q of M plus 1n going to the center. There's our arrow coming in right there. And there's our Q of M minus 1n going into the center right there. So that is our arrow going in right there. So again, recall top is looking at just our material A, and the bottom is looking at material B. So this is just dealing with material A, and this is just dealing with material B, whereas these guys right here are dealing at the interface between both materials. So now what assumptions can we make? Well, we can assume it's steady state, two-dimensional heat transfer, no heat generation, and negligible contact resistance from what they told us in the problem statement. So from here, what we want to do as we begin our hand solution is to create our setup page. So now let's create that setup page. So we read through our problem statement, we looked at our initial given diagram, we understand everything they've given us, everything they asked us to solve for, and what assumptions we're going to be making right here. So this is problem number 442. In our given information, I'm going to redraw out our diagram right here. So this is a simplified version. I've drawn out by hand right here. There's my center point, Mn. Here we come out here to M plus 1n, up here to M, comma n plus 1, over here M minus 1n, and down here below is our M, comma n minus 1 right there. We can see the width right here is our delta x, our length right here is our delta y. We also know that our distance between these 2 points here would be our delta y right there, and the distance between these points going right here, all our nodes right there, would be our delta x right there as well. We can see the top right here, that's our material A, our thermal conductivity K sub A. Down here we have material B, thermal conductivity K sub B right there. So what are they asking us to solve for? Well, there's two parts to this problem right here, part A and part B. Let's look at each of these separately. For part A, they want us to find expressions for the control surface heat rates right there. So we want to find these Q values, our heat rates right there. So going from each of those four nodes into our center node, we want to find those heat rates. So we have our heat rate from our M minus 1n going into our Mn right there. So there's our equation, what I'm going to call equation number 1 right there. Then we're going to go from Q of our heat rate for our Q of M plus 1n right there. So let's go up here, Q of M plus 1n right there going into our center node Mn right there. So that's our heat rate that I'm giving by equation number 2. Then we're going to go for our Q right here, our heat rate now of Mn plus 1. So that's this point right here going down into our center node there. So that's equation number 3. And last, we got our heat rate here from Mn minus 1 down here up to our center right there, Mn. And that I'm going to call our expression number 4. So those are our 4 expressions that we're solving for, and I've clearly labeled them out. There's a lot of different moving parts to this problem right here as we're going through our solution, and having them labeled and numbered like this is going to make our life easy. We can always flip back to the setup page and get this information. It's a great place to have this organized in a manner that we can understand what we're looking for. Now that was part A. Now for part B right here, we want our finite difference equation at that center node Mn right there. So we have some procedures. So now that we can kind of think about in the back of our mind how we're going to solve for part B, we know we're going to need our information we solve for in part A in order to get that value right now for our finite difference equation at this node Mn for our part B. Assumptions again, steady state, no contact resistance, 2D heat transfer, and no heat generation right there. So those are going to help simplify down our solution. So now moving on to our solution right here, we want to take a look at conduction to that node Mn. So let's derive expressions for the control surface heat rates first. Now let's break this down in individual parts. We have our diagram right here. I've redrawn out my diagram over here on the right there. Well, let's do the simplest parts first, which is just dealing with one material at a time. That's something we're used to, something straightforward. We'll just think of it as one individual separate part to the problem right here. So let's just deal with our material A only. So we'll deal at the top right here. So that's just dealing with this node right here for our material A only. So for this one right here, we can come up with our governing equation. Now our governing equation for this part of the problem right here comes from equation 4.33 on page 244 of our textbook. So with that one right there, we come up with this general expression right here. Where now our heat rate for M of N plus 1, because that's this point right here dealing with material A only, going in towards now our center right there, Mn right there, is equal to our K value right here, our thermal conductivity for A, times, this is our general expression, so I haven't put that in for A yet, times my delta XL right there, times now this relationship here for our temperature difference over our delta y right there. So a temperature difference of this node right here to our minus our center node right there, temperature of Mn right there. Now, specifically for our system right here, we want to look at this for material A only. So for our specific problem, we can plug that in right there. So we have our heat right here now for that node right here, our M of N, or sorry, our node of M comma N plus 1 right there, going to our center node Mn right there. This is equal to, now we can plug in our value right here. This is our thermal conductivity for material A, times the length right there, that's given the problem statement as well, times now we can move this delta Y out over here under our delta X, pull this out front. This is delta X over delta Y, which would be the distance between those nodes in our X and Y direction, or the shape of this square right here, like that there, times our temperature difference between those two nodes. Now if we go back to our setup page, this is the expression we needed to solve for number 3 right there. So if we've done that now for this node number 3, next now we want to do this for material B only. So this was for material A only for node number 3 right there, or expression number 3 right there. Let's do this now for material B only right here. So if we're looking at material B only, we come down here to this node right here, M comma N minus 1. Now we can go to our textbook here to find our governing equation. This is equation 4.34 on page 244 of our textbook, where we have this general expression right here. Again, we want to start with the general equation as we start out with this here. So this is our heat right here for that node down here, our Q of M N minus 1 right there, going to our center node. So now we're going up right here to our center node right there. And this is equal to our thermal conductivity. Again, in general form, we're going to leave this as K. Now this is going to be times our delta XL right there, times now our temperature difference between that node right here, temperature of M comma N minus 1, to minus our temperature of the center node right there of temperature of M comma N right there. And this is all going to be divided by our delta Y right there. Plug this in for our specific problem right here, and this is for material B only. So now our thermal conductivity K value is now a K sub B. Everything else remains pretty much the same, other than the fact that we see this as delta Y. We can move out and put it in front of our delta, underneath our delta X right there. So now we have this times L times our delta X over delta Y times this temperature difference between now this node right there, M comma N minus 1, minus temperature of our center node right there, T of M comma N. And this relates back on our setup page to expression number 4. So as we look at those governing equations that we utilized here from our textbook 4.33 and our 4.34 right there on page 244 of our textbook, I want to take a look at some of those individual sections within those expressions right there. So if we take a look at our quantity right here, our delta YL, or in this case our delta XL right here, for this one right here, this is going to be the heat transfer area. Our Q is going to be our heat transfer rate, and our K is our thermal conductivity. And this last term over here, right here, this is going to be the finite difference approximation to the temperature gradient between the boundary and the two nodes right there. So just a little side note, looking back at our governing equations, relating it to what we saw earlier within this module as we're going through some of this theory and these governing equations. So now the next thing we want to take a look at now is conduction to that center node Mn that occurs in both materials A and B. We've already done this for A and B separately, but now what about those other two nodes that occur in both materials? So what we can do now is we can take a look at the conduction now from our M minus 1n to our center node right there. So this is our M minus 1n right here to our center node right there. So now we're going to look at the heat rate right there. Again, we're dealing with conduction right there. But what we still want to do, though, is separate this out. Even though we're dealing with it in both materials A and B right there, let's look at each of these separately. So we'll solve it first now for find our heat rate expression right here for just material A right there. So Q of A from this M minus 1n node right there to our center node right there is going to be equal to our thermal conductivity. And this again comes from our equation 4.31 on page 244 of our textbook. Now we're now plugging in for our material A right there, our thermal conductivity K sub A times that L times now what we need to look at, this is delta Y over 2 over delta X times the temperature difference between our M minus 1n node right there and our temperature at our center node right there. So the difference also right here is this delta Y over 2. And the reason that is right there, if we look at that distance from there to there, this is a delta Y over 2 because the whole distance is delta Y. So this distance is just the A term right there, just material A right there is going to be the delta Y over 2. So now we're going to do the same thing as we take a look at material B right here. And this is going to tell us now that our Q sub B right there for just looking at material B, as we're going from that same node right here over to our center node right there, is going to be equal to our K sub B now, our thermal conductivity right there for K sub B for material B right there, times the distance L, times again now our Y over 2. And that Y over 2 is from this distance right here. We're just dealing with half of this delta Y distance right there. So delta Y over 2, all divided by our delta X terms. Our delta X right there is still going to be that that full distance from there to there, which is our delta x term right there, times the temperature difference between our node right here and then our center node right there, which is expressed right there. So now that we've gone through and found that heat rate for material A and material B separately, we want to add those together because the total is going to be the sum of A and B. So now we can notice here our heat rate going from our node M-1n to Mn right there, our total heat rate is going to be the sum right here of QA and QB right there from that node to the center right there. So you notice right here there is no subscript, no indice there, whereas this is B and A right there. So this is equal to now, the total right there is going to be equal to our Q sub A going from M-1n to Mn plus Q sub B going from M-1n to Mn right there. So plugging in our values from above into these two expressions, or for these two expressions right here, we can find now that our Q of M-1n going to the center node right there is equal to our K sub A times L times now when we plug in right here our delta Y over 2 delta X times that temperature difference there, plus now for material B, K sub B L times that same delta Y over 2 over delta X minus the temperature difference there. So now we can combine, reduce, simplify, and pull some things out. So what we find out here now is our Q going from M-1n to our center node M comma n right there is equal to the sum of those two thermal conductivities, K sub A plus K sub B right there, times our L value right there, times now this is common for both of those, so delta Y over 2 divided by delta X times that same temperature difference right there. And this is going to now give us an expression that we're going to refer to as expression 1. Again, expression 1 is our heat rate going from there to there. So now if we continue on, and we still want to look at our conduction occurring in both materials A and B, we now need to consider this node over here. So we want the conduction from this node M plus 1n to our center node Mn right there. So we're coming in like this right there for that conduction term now to find that heat rate. So this we can go back to our governing equation from equation 4.32 on page 244 of our textbook right there, where we have this general governing equation here. So this says that our Q value, our heat rate from this node over here, M plus 1n, going to our center node Mn, is equal to our thermal conductivity times our delta YL times our temperature difference between those two nodes, all divided by our delta X there. So again, even though we're dealing with both materials for this right here, we want to look at A and B separately and then sum them together. So that's the same thing we do there. Let's look at just material A. So this says our heat rate for material A from this node right here, M plus 1, n to our center node Mn right there is equal to now our thermal conductivity of Ka times L, and it's still that delta Y over 2 because we're just looking at this distance right here, half of that delta Y right there, all divided by our delta X right there because it is that full delta X distance going across that node right there. So now we can say this is times our temperature difference between those two nodes, T M plus 1n minus T of Mn right there. Now we do the same thing for material B. We can say our heat rate for material B from that node M plus 1n going to our center node Mn there is equal to our thermal conductivity K sub B times our length L right there, times now again that same delta Y over 2 divided by our delta X again because that's just delta Y over 2 for that distance there, but our center distance right there is still our delta X right there, times that same temperature difference of temperature at node M plus 1n minus temperature at node Mn right there. And again, same thing that we did previously. We now can sum those two together to get our total heat rate right there for Q of M plus 1n going into our node right there in the center of Mn right there. So we do that and plug those values in for that right there. So here's our general governing equation saying the whole thing is equal to heat rate of A plus the heat rate of B for those two nodes right there. Plug in our values to these two expressions right there from above. Our Q sub A and our Q sub B right there from our node M plus 1n to our node Mn right there. Plug that in. We end up with this expression right here. So our Q value, our heat rate from that node M plus 1n to our center node Mn is equal to our KAL times our delta Y over 2 over delta X times our temperature difference between those two nodes, plus our KB thermal conductivity times our delta Y over 2 over delta X times the temperature difference between those two nodes. We reduce that down, we simplify it, we see now our K, our total K heat transfer rate there from N plus 1n to our center Mn right there is equal to the sum of those two thermal conductivities, Ka plus Kb right there, times that distance L, times now our common delta Y over 2 divided by delta X times the temperature difference between the two nodes will give us now our final expression number 2. So now we have expressions for 1, 2, 3, and 4. So now we've completed part A for our problem right there, and we need to move on to our solution to part B. So for part B, we want to find our energy balance on our node, our center node, Mn. Now we can do this by looking at our general governing equation, 4.30 on page 243 of our textbook right there. Now we saw this earlier with our module right there. We have our E dot In plus our E dot G right there equal to 0, but we've now made the assumption in our problem statement, we can go back to that setup page and see that there is no heat generation for this problem here. If there's no heat generation right here, then this term disappears, goes to 0, so we're simply equal to 0 right there. So our E dot sub In right there is equal to 0 right there. So we're just going to sum 1 plus 2 plus 3 plus 4 together, and that's going to equal to 0 right there. So we can plug this out in general terms right there. Our Q of M minus 1N to our center, our heat rate for going from that node right there to our center node, plus the heat rate from M plus 1N to our center node, plus the heat rate from M comma N plus 1 to the center node, plus our heat rate from our M of N minus 1 to our center node. All those summed together is equal to 0. Well, now we have expressions 1, 2, 3, and 4 from these up here that we solved for in part A, and we can plug those straight in. And we do that there, we end up with is we have this value right here of our Ka times our delta X over delta Y times now our temperature difference between T of M N plus 1 minus T of M comma N right there, plus our Kb, our thermal conductivity B, times that delta X. So over our delta Y right there of our T of M comma N minus 1 minus the temperature between those two of our center temperature there, plus now our combined K of A plus B right there, times our delta Y over delta 2 over delta X right there, times now that temperature difference of T of M minus 1N plus T of M plus 1N minus 2 times our Tmn right there. We combine those all together for those last two terms right there. It's all equal to 0. So this is what they asked us to solve for in part B, was to come up with that expression for our energy balance on that center node Mn, utilizing what we solved for in part A. Now I've also included for your reference here a typed out solution so you can take a look at these, and I've referenced the governing equations so you can go back and double check those. And I think this would be good practice to go through and do what I did, solve it by hand, and make sure that you come up with the same equations and same little solutions as well using those governing equations. So here's again now the same thing, but now for both materials right here. And again, I have these all typed out for you, and you can go back and reference these as well. So let's take a look at another example problem right here. So now let's take a look at example problem 4.41 from our text right here. So within this problem, they're telling us here that one of the strengths of numerical methods is the ability to handle these complex boundary conditions. So let's take a look at a slightly more complicated boundary condition within this example problem here. So in the sketch below, we can see the boundary condition changes from a specified heat flux right here, which is our Q double prime S right there, to convection right here. We can see there's our convection term over there, our H T infinity right there. And this occurs at the location of our node right here, our center node right here, our M comma N right there. So what they want us to do within this problem now is to write a steady state, two-dimensional finite difference equation at this center node, M sub N right there. So we can see, okay, there's our heat rate right there. There's our convection going on right here. We can see we have a delta X going here and our delta Y right there. And there's our center node right there. So looking back at that problem statement, let's simplify that down just a little bit here and kind of get a little bit of procedure for analysis, an idea of how we're going to tackle and solve this problem right here. So what do we know? We know that the boundary conditions are going to change from a specified heat flux on one side of that node to convection on the other side of that node right there. Now, what are they asking us to solve for? They want us to find the finite difference equation for the node at the point where the boundary condition changes from that heat flux to convection. So there's our center node right here. We're going to redraw our schematic right here with a little bit more detail on it right there. There's our heat flux right there. There's our convection term right here. We also have three other nodes. We have this node right here, which is our M minus 1N. We have this node right here, which is our M plus 1N. And we have this node right here, which is our M N minus 1 node right there. So what we can see now with this right here is the distance between this node and this node right here is our delta X, which is the same distance as this node and our center node there. And the distance right here between these nodes down here to this node at the bottom, our M comma N minus 1 node, is this delta Y distance right there. Now looking at this right here, if we're going into this other node right here, there's our distance right here now of Y over 2. So just half of that distance right there going down into there. But we have this whole distance right here. If we're looking at this bounding box right here, there's our delta X right there. So it has a bottom surface layer here and a top surface layer of delta X, but it's got a height right here of a delta Y over 2, because that's going to be half of this delta Y distance between those nodes right there. Now we can see coming in, we have a Q1, a Q2, a Q3, Q4, and a Q5 right there coming in to this area that we're interested in, surrounding our node right there, M comma N. So what assumptions can we make from our problem statement? Well, we can assume it's going to be two-dimensional. It's going to be steady state conduction with no generation, and it's going to be constant properties. So we're not dealing with two different materials now, just one material. So now that we've looked at this, we've read through a problem statement, we really get an idea of what's going on at those nodes right there and how we're going to label them. We have a little bit of an idea now for a procedure for analysis. So let's move forward and start our hand solution. And the first part of our hand solution is to create our setup page. So we create our setup page, we read back through their problem statement, we look back through that procedure we just went through. This is problem number 4.41. What are we given? Well, we have a specified heat flux, our Q sub S double prime right there. We have a convection heat transfer coefficient, our H value there. And we also have a T sub infinity for our temperature of the surrounding area right there. So I redraw out this by hand right here. There's our center node right there, Mn. There's our node out here of our M plus 1n. We have our node over here of M minus 1n right there. And we have down here our bottom node of M comma N minus 1. We know this distance right here between those nodes is delta x, and this distance right here is a delta y right there. We can see there's our heat flux right there. There's our convection right there. We now have our Q3, our Q1, our Q2, our Q4, and our Q5. And again, we know that this distance right here, we can see there's our delta y right there as well. So what are we assuming? We're assuming it's going to be 2D. Steady state conduction, no generation, and constant properties. So that's going to simplify down our solution quite a bit. What do we want to find? We want to find the finite difference equation. So we're going to have the same type of procedure we saw in the previous example problem right there. We're going to go through and solve for Q1 through Q5 in this case now, and then from there we can use that to find our finite difference equation for our center node, Mn right there. So now as I use that setup page and begin my solution right here, I want to come up with my governing equations, but I also want to redraw out my diagrams in a manner that they're easily to view. So I draw this out a little bit bigger and a little bit neater up here so I can clearly see all of my nodes right there, clearly labeled. I have all my Q values right there, my Q1, Q2, Q3, Q4, and Q5. And I also have right here my heat flux coming in right there, my Q sub S double prime right there. I have my dimensions, my delta Y, my delta X right there. Then I zoom in a little bit just on this area, leave it alone by itself right there, and I can see, well, there's my heat flux right there, there's my convection right there, there's my Q1, my Q2 right there, and we can see now we have our individual nodes right there, our Mn in the middle, our M minus 1n over here, and our M plus 1n right there, and I have all my dimensions. That's delta x right there, well, and that's delta x over 2 and delta x over 2 right there, and for this right here, this is going to be my delta y over 2. Now, what I want to recall from our governing equation, we have this relationship right here where Q is equal to Q double prime A, where Q is the heat transfer rate in units of watts, and my Q double prime right here, this is my heat flux in units of watts per meter squared right there, and A is my area in units of meters squared. So I have this relationship here. If I want to get my Q, I can take that flux right there, my heat flux in units of watts per meter squared, multiply it by area, which has units of meter squared. We can see my meter squared cancels with my meter squared, gives me just watts, which would give me my Q value right there, or my heat transfer rate in units of watts. So utilizing that relationship right there and that equation right there, what I can do now is I can say, well, if I want my Q1 right here, my Q1 right there, what I can do is I can say, well, I can take my heat flux right here, my Q sub S double prime times my area right there, and that'll give me my Q1 right there. So I can take my QS double prime right there, my heat flux that's given to me in the problem statement, times my area. Well, what is my area? Well, my area right here is going to be my delta X over 2 times my L distance right there. So there's my delta X over 2 times my L distance right there to give me that area term that I'm going to multiply by my heat flux to get my Q1 right there. So now that I have that value for Q1 right there, what I can do now is move on to my governing equation for the beginning of my solution of the problem. So we can go to our equation 4.40 on page 245 of our textbook. Looking at now, we're going to start with convection. So we can start with our convection term right over here. So this right here relates to our Q2 right there as we're dealing with convection. So we've already done our Q1, now we're moving on to our Q2 right there. So for Q2, we have that governing equation, which our general form of this equation goes right here, where we have our Q of infinity right there going in now, so to our Mn right there. So that heat rate right there is equal to our H value from this governing equation 4.40 right there, times our delta X over 2, times our L distance right there, times our temperature difference of our surrounding temperature, minus the temperature at the node, plus right here now we have our H value times our delta Y right there, over 2 times our L value times the temperature of surrounding temperature to our node Mn right there. Well, what we can see right here is we're just concerned about this surface right here, not this surface over there. So this term goes away. We're just left with this term right here. And what we can see now, our Q2, this reduces down to for our expression right here of H times our temperature difference between our surrounding temperature and our node right there, our node temperature T of Mn right there, times our delta X over 2 right there, times our L value right there, which now gives us an expression for Q2. So now we have an expression for Q1 and an expression for Q2. We still need to solve for Q3, Q4, and Q5. So now let's solve for our heat rate expressions for Q3 and Q4. So we can take a look at this right here. We redraw out this diagram right there. Now we're looking at Q3 and Q4 right there and right there. So the surface that we're dealing with for Q3 and Q4 is this delta Y over 2 times our L distance right there. So this is our delta Y over 2, and our L distance again goes back into the board if we're looking at this in 3D right there at some distance L like that there. So what is our governing equation going to be? Well, we can look at equation 4.31 on page 244 of our textbook right there, and we can say now from our value right here, if we're looking for our node m minus 1n right there, going to our center node Mn right there, we have this expression that Q of m minus 1n to our Mn right there is equal to our thermal conductivity right there, times our delta Y distance right there, times L right there, times our temperature difference from that outside node to our inside node, all divided by our delta X term right there. So let's plug in for our specific problem right here, where this was going to be a delta Y over 2 right there for our specific problem, because that's the distance we're dealing with right there. So our Q3, as we plug in for our specific problem right here, is equal to our K value times now our delta Y over 2, move this delta X over as well, all over 2 delta X right there, times now our temperature difference between our T of m minus 1n and T of Mn right there times our L right there. So again, this 2 on the bottom comes from the fact that this is now a delta Y over 2, and our delta X comes from moving this delta X over right there. So now we can look at our other node over here, our m plus 1n coming into our center node right there. Look at our heat rate equation there, and this comes from equation 4.32 on page 244 for our general equation, going from that outside node to the inside node, or m plus 1n to our m comma n right there at the center right there. So our heat rate from m plus 1n to our mn right there is equal to our thermal conductivity times our delta Y times L times our temperature difference between those two nodes, all over our delta X. Where now for our specific problem, this is our Q4 right there. There's our Q4 right there. Our Q4 going in right there, and this is equal to our thermal conductivity K times that delta Y over 2, moving our delta X over right there. There's our delta X as well that moved over from the bottom. This is times L times that temperature difference now between our temperature at our T of m plus 1n minus our T of Mn right there. We can reduce this down and simplify just a little bit, and we can say our Q sub 4 is now equal to our K times our delta Y over 2 delta X times that temperature difference between T of Mn comma n minus T of Mn times our L value right there. And now this gives us an expression for 3 and 4. So far in our solution, we have a Q1, Q2, Q3, and Q4. The only one we don't have now is our Q5 that we can solve for. So now solving for our heat rate for Q5, we can go to our equation 4.34 in our textbook, going from m of n minus 1 to mn right there. So mn minus 1 to mn right there in our diagram. So I've redrawn out again here. So that's our Q5 right there. So our general expression for that equation is given to us from that equation 4.34 as Q of m comma n minus 1 to mn right there, equal to our thermal conductivity K times our delta XL right there, all times our temperature difference from that node to our center node, all over our delta Y. So now you can notice that our delta X and delta Y have switched, because now we're coming in a different direction, going up in our Y direction right there. So we'll plug in for our specific problem. Our Q5 is equal to our thermal conductivity K times our delta X over delta Y, when we move this delta Y over there like that, times our L value right there, times now our temperature difference from our node right here, our T of Mn minus 1, minus our T of our temperature node right here, at temperature of T of M comma N right there. So now we have a value for Q1, Q2, Q3, Q4, and Q5. So now we can move on to our energy balance, where in our case here, our delta X is equal to our delta Y for the specific problem that we're working on here. So we go over the energy balance equation. What we have here is our Q1 plus Q2 plus Q3 plus Q4 plus Q5 is equal to 0. So what I've chosen to do is to rewrite out all those values for all of my different Q values right there, 1 through 5, because these are scattered throughout our solution right here. I'd like to have them all in one neat nice place so that I can plug this together into our energy balance equation here. So I know that my Q1 is equal to my heat flux right there times my delta X over 2 times L. My Q2 is equal to my H value here for convection times our delta X over 2 times L times my temperature difference between my surrounding temperature and that node temperature there. My Q3 is equal to my thermal conductivity times my delta X over 2 delta X. Those delta X's will cancel actually right there, times an L value times the temperature difference between the nodes. So I can reduce that down, cancel those X's, equal to K times my L over 2. When I combine this L, put it up top there, times now my temperature difference between my temperature at node M minus 1N and my center node T of Mn there. Similar for K4, I have my K times my delta X over 2 delta X. The delta X's again cancel, times my L value there times my temperature difference between the two nodes. Rearrange and simplify, this becomes K times L over 2 times the temperature difference between those two nodes. And then Q5 is equal to K times delta X over delta X. Well, that whole term cancels out to 1 right there. So this is times L times the temperature difference there. So this reduces down to, for Q5, my K value times L times the temperature difference between the node of T of M N minus 1 and my center node right there, T of M comma N. So that gives me now those expressions for Q1 through Q5 simplified down. And I can plug that back in now to my energy balance equation. So that's exactly what I do there. And I write this all out. We can reference back to our previous page right there. There's my Q1 plus Q2 plus Q3 plus Q4 plus Q5. All is equal to 0. I can reduce and simplify down because I notice that I can pull out a K times L over 2 right there, pull that out in front right there, and what I end up with this reduction here, because this will end up putting in a K on some of these right there on the bottom right there of these first two expressions right there that didn't have them in it for Q1 and Q2, and I can say that this is all now equal to 0 when I pulled those out, and I can divide both sides by that K times L over 2 to eliminate it, and I end up with this simplified expression down here for my energy balance, which is the answer for this problem that they'd asked us to solve for. And again, I've included the typed out solution for you to reference back to with the equation numbers as well.